Dear students, I am Dr. Tamrakar from Bharati College of Engineering and Technology. I am teaching food machinery in B 5th semester. Today we will do our next class. We will discuss the force exerted on a series of radial curved vane. Here we have to see this figure. This is the inlet triangle, this is curved vane, and this is next, this is previous. A series of curved vanes are there. The radius of this inner is, that is outlet triangle, is R2 and inlet triangle is R1. Here the inlet triangle is developed as the series of plane blades or plane vane. Then this is V1, VR1, VF1. This angle is alpha, this angle is theta, this is VF1. This is tangent at point P, and at the outlet side, this is outlet triangle, means water flows from here and striking this blade, and then outlet from this side. Then this blade moves to this place, and next blade comes in front of the jet. Okay. Then here this is the outlet triangle, VR2, V2, VF2, and this is angle phi and beta. This is U2, this is VW2. Now R1 is radius of wheel at inlet of vane, R2 is radius of wheel at outlet of vane. Here omega is angular speed of wheel, and as we know V equal to R omega, so this U1 equal to omega R1 and U2 equal to omega R2. Now the mass of water striking, mass of water striking per second for series of vane equal to mass of water coming out, mass of water coming out from nozzle per second, from nozzle per second, that is equal to rho A V1, rho A V1, where A is the area of jet, and V1 is the velocity of jet, Moment of water striking per second, moment of water striking per second, the vane in tangential direction per second, the vane striking the vane the when in the tangential direction per second, in the tangential direction per second at inlet equal to mass of water per second equal to mass of water per second into component of V1 in tangential direction. In tangential direction. So here mass of water striking per second is rho A V1 and tangential direction is VW1. As we know, component of V1 in tangential direction is V1. As we know, V1 in tangential direction is equal to component of V1, that is V1 cos alpha, and that is equal to VW1. This is from the figure. Now similarly momentum of water striking at outlet of water at outlet per second, is equal to rho A V1 into component of V2 in tangential direction into component of V2 in tangential direction. So this is rho A V1 and minus V2 cos beta So this is minus rho A V1 V2 cos beta. As we know, V2 cos beta is equal to VW2. So we can replace this V2 cos beta by VW2. Now, angular momentum per second at inlet, angular momentum per second at inlet is equal to momentum at inlet into radius at inlet. That is equal to rho A V1 VW1 into R1. This is W. R1. And angular momentum per second at outlet, angular momentum per second at outlet is equal to moment at outlet into radius at outlet. So this is rho A V1 minus in mass action V W2 into R2. Now torque exerted by torque exerted by the water on the wheel, water on the wheel, that is capital T, equal to rate of change of angular momentum, rate of change of angular momentum that is equal to initial angular momentum per second, initial angular momentum per second minus final angular momentum per second, final angular momentum per second that is equal to, putting the values, rho A V1 VW1 R1 minus rho A VW1 VW2, so AV1 into VW2, and that is R2 into R2. Now this minus plus, and taking rho A V1 as common, so here rho A V1 common, VW1 R1 plus VW2 R2, and next is work done per second on the wheel. So this is the formula for the torque exerted by the water on the wheel. Now we have to calculate the work done per second. Now work done per second on wheel, work done per second on wheel is equal to torque into angular velocity. Angular velocity, that is equal to T omega. Putting the values rho A V1 V W1 R1 plus VW2 R2 R2 into omega. Now rho A V1 into VW1 R1 omega VW1 R1 omega plus VW2 R2 omega. But as we know, U1 equal to omega R1, as we know U1 equal to omega R1 and U2 equal to omega R2. Putting this value of U1 and U2 here, this is rho A V1 into V W1 U1 plus V W2 U2. This is the value of work done, and if the angle beta in the above equation is obtuse angle, if angle beta is obtuse angle, then the equation will be equal to this. Work done will be equal to rho A V1 into V W1 U1 minus VW2 U2. This is the equation for beta is obtuse angle. So the general expression of work done per second on wheel, work done per second on wheel is equal to rho A V1 V W1 U1 plus minus V W2 U2. This is the final general expression for the work done if the discharge is radial at outlet, when discharge radial at outlet on this condition the beta equal to 90 degree, beta equal to 90 degree. So this work done is equal to rho A V1 V W1 U1 when the outlet is radial. This is the equation, because here VW2 is equal to 0, because here VW2 equal to 0. So this is the equation for. Now efficiency of the radial curved band of radial curved band when here, as we know, efficiency equal to output by input. So here this is output is work done per second, work done per second by input is kinetic energy per second, kinetic energy per second. Now putting the values, that is rho A V1 V W1 U1 plus minus VW2 U2 is divided by half of mass per second, mass per second into V1 square. Now rho A V1 V W1 U1 plus minus V W2 U2 is divided by half mass per second is rho A V1 and V1 square. So here this rho A V1 cancel with rho A V1 and now the value comes 2. This is 2 V W1 U1 plus minus V W2 U2 is divided by V1 square. V1 square. This is the equation of for the efficiency. If there is no loss of energy when water is flowing over the vein, the work done on wheel per second is also equal to the change in kinetic energy of the jet per second. Hence, the work done per second and on wheel is also given as work done per second on wheel equal to, this also can be done as work done per second on wheel per second on wheel can also be calculated as change of kinetic energy per second of jet, change of kinetic energy per second of jet. So that is initial kinetic energy minus final kinetic energy, initial kinetic energy minus final kinetic energy per second of the jet, per second of jet So putting the values, initial kinetic energy half of mv1 square, half of mv1 square minus half of mv2 square. This is mv2 square. So here that is taking half m common, v1 square minus v2 square as we know mass per second equal to rho a v1 as mass per second equal to rho a v1. Putting the values here, half of rho a v1 square, and this is v1 square minus v2 square hence the efficiency is equal to work done per second on wheel by initial kinetic energy per second of jet. Initial kinetic energy per second of jet. So this is half of rho a v1 square into v1 square minus v2 square is divided by half of rho a v1 square into v1 square. Now this value comes as v1 square minus v2 square by v1 square, that is equal to 1 minus v2 square by v1 square. From the above equation, it is clear that for a given initial velocity of jet v1, the efficiency will be maximum when v2 is minimum. When v2 is minimum, the efficiency will be maximum. But v2 cannot be zero, as in the case for the incoming jet will not move out of the van. Also gives efficiency of the system. Now from the equation, it is clear efficiency will be maximum when VW2 is added to VW1. VW2 is added to VW1. In this condition, this is only possible when beta is an acute angle. When beta acute angle, that in that case VW2 equal to V2, VW2 equal to V2, and angle phi will be 0. Angle phi will be 0. But in practice, phi cannot be 0. Hence for maximum efficiency, angle phi should be minimum. This is minimum. Okay. Now, next classes we will start some numerical on this.